Okay, so the next component of Earth system sciences that we explored was the Earth's interior, right, and plate tectonics. And so we started with kind of a historical discussion of the thinking and how it progressed throughout the 20th century. Um, and that started with this guy, Alfred Wegener, a German scientist in the early 1900s that first proposed the idea of continental drift. It was largely not accepted, largely rejected by the scientific community. Um, an individual named Arthur Holmes did come along in the 1930s, as this slide says, and suggested that there perhaps was convection occurring in the mantle, I think largely based on theoretical calculations. And he suggested that perhaps that could propel continental drift that Alfred Wegener had proposed some 2 decades or so earlier. Um, Evidence for that didn't come for another 2 decades, and it came in the form of paleomagnetic data, or really magnetic data on the seafloor initially. And we talked all through that, but that discussion really requires that we understand what the Earth's interior looks like, and how paleomagnetism works, or how the magnetic field is even generated in the first place. And so, moving to the iPad, we said that the Earth has a structure. Its interior is differentiated into a core, which is made up of metallic iron and nickel, and we have a mantle, which is made up of silicate rocks. And so that's drawn here on the iPad. It's shown down here in a variety of slides. But the interior is divided into two separate layers of core, the inner core and the outer core. The inner core is solid and the outer core is liquid. And because of the flow in the outer core, there is some amount of circulation, something like that. Excuse me. There's some amount of circulation in the outer core, and anytime you have two metallic substances moving past one another, electricity and magnetism are generated as a result. Magnetism in this case is generated. It produces a large magnetic field that we experience on the Earth, and a magnet has field lines, right, that look something like that. And so we showed, oh gosh, where is the slide with it? Well, here's a slide. I think it's actually, yeah, it's hiding behind that. Let's get rid of that. Okay, so we have a magnetic field, and it looks something like that. And the important thing to note here is that the magnetic field lines don't intersect the Earth's surface at the same angle everywhere. Up here at the poles, my mouse is down here on the PowerPoint. Up here at the poles, the magnetic field intersects the Earth's surface at a right angle, at 90 degrees. But out here at the equator, it actually hits the Earth's surface roughly parallel. Okay, and that's shown in the pink field lines drawn on the iPad there. And if we draw in the angles of intersection, you can see clearly they vary dramatically from low latitude to high latitude, right? And so there's a little compass arrow drawn on the map that's kind of in the mantle there on the right side on the Earth, and it's reflecting the declination of a compass needle, which is the quality of pointing north. That property we call declination, pointing toward the North Pole. But it also has this other property, the inclination, and that reflects or refers to that angle that it orients itself in, right? Reflecting the intersection angle of those field lines with the surface. And that gives you information about the latitude of that compass needle, or in the case of paleomagnetism, of an iron-bearing mineral that preserved the magnetic field that was present when that mineral crystallized and cooled. Excuse me. Okay, and so we talked about that, about this fact that iron-bearing minerals can preserve magnetic properties, and they can orient those magnetic properties to the field that they exist in when they're above a certain temperature, this temperature called the Curie point. When they're below that temperature, though, they're not able to reorient themselves. And so if the magnetic field were to change, after an iron-bearing mineral had cooled below the Curie point, it would not respond to that, right? It would need to be heated back up in order to inherit those new properties. And so over time, as uh, volcanic eruptions occur and these iron-bearing minerals, these mafic minerals, crystallize, they preserve the magnetic field. And so we can go back into the record and reconstruct that ancient record, and people have, and it serves as kind of a barcode of these magnetic reversal events. Okay, and again, the magnetic reversals just have to do with changes in the orientation of these currents that are indicated by the arrows on the now pink iPad there, because the connection is kind of fuzzy. Those arrows indicating convection within the outer core, that kind of light tan interval, and those are not necessarily the currents that would exist. They're just sort of there schematically to indicate that there is flow. Okay, and so the magnetic field exists and it intersects the Earth's surface at different angles depending upon latitude. The declination of a compass points north. The inclination reflects that angle of intersection of the field lines with the Earth's surface. Okay, and so the next video we'll jump into the record of seafloor spreading and how that relates to magnetics.